Okay, so before we do lines and planes in 3D, you should know the 3D coordinate system, which we already spoke about several times. So in the 3D coordinate system, there's the right-handed one and the left-handed one, but we'll always stick to the right-handed one, where for the right-hand one, you have your right hand make a make three axes like this, and then it has to be rotating in the counterclockwise direction, say x, y, and z. That's the direction. Okay. Yeah. So another way to say it is like you have the xy plane, and then use your right hand to determine the z-axis. If the z-axis is not the right-hand one but the left-hand one, that's the left-handed coordinate system. Okay, so you're using the right-hand coordinate system, and then we'll have something like 1, comma 2, comma 4, or something. This point would be first going one step in the x direction, and then going 1, 2 steps in the y direction. That would be y. And now you go up 4 up in the z direction, so that this point right here is 1, comma 2. Okay. So that's the coordinate system we were talking about. Now, in 2D, if we have x equals to 1, what kind of graph do we get? Yeah? You get a vertical straight line. You get a straight line that's vertical. So here's the y-axis, here's the x-axis. And the reason is, if you say x equals to 1, that means you're taking every point on this plane whose x coordinate is 1. Right? What are some examples of points that have x coordinate as 1? You have 1, comma 0 here, 1, comma 1, 1, comma 2, 1, comma 3, 1, comma negative 1, 1, comma negative 2. You also have like 1, comma 1/2. So if you take every point that has x coordinate as 1, you end up having all the points here, and then if you collect them, you end up with this straight line. That's what you get, right? That's why x equals to 1 is a vertical line. Okay? If you take that viewpoint, now here's a question for you to think about. In 3D, x equals to 1 gives us what? Take a guess. Huh?
A plane.
It will be a plane. What kind of plane would that be? Well, let's see. Here's x, here's y, here's z. And x equals to 1 means we are collecting all the points whose x coordinate is 1, right? So what are such examples? You have 1, comma 0, comma 0. You don't go any direction in y or z, you just stay here, right? But you could also do 1, comma 1, comma 0. 1, comma 2, comma 0, 1, comma negative 1. If you do that, then you get this vertical line. But you also have the z-axis that you can arbitrarily set, right? So you can have 1, comma 0, comma 1, which means you just go one step here and you just go up by 1. Or you can do 1, comma 1, comma 1, which will be this one. So if you set z as 1, you get all this line that's passing through the height 1. Now, if that picture doesn't really click, then think about it like this. Here's x, here's y, here's z, right? Setting x equal to z means you just go one step in the x direction, but x and y and z are anything you can think of. Okay, so it could be this point itself, it could be going up or down or left or right or some other place. All you require is that the x coordinate has to be 1. So if you do that, you end up with this plane. Can you describe this plane? It's a plane first. X equals 1 is a plane passing through through 1, comma 0, comma 0, of course, right? and is parallel to, okay, it's parallel to what? It's parallel to, what's this other plane that this is parallel to? Here's what you have, right? This plane is parallel to, yeah?
The z-axis.
It is both parallel to z-axis and the y-axis. So one way to say it is that it's parallel to the zy plane or yz plane, and it's parallel to yz plane. Yet another perfectly okay way to say it is, you can say another way to describe this will be a plane passing through 1, 0, 0. Well, this could be like 1, 1, 0, 1, 0, 1, or anything else is fine. But 1, 0, 0 is the simplest, so that's why I choose that. Now that part is the same as before, but now I'm going to say perpendicular to the x-axis. Perpendicular to the x-axis. Right? That's the plane that x equals 1 gives you. Now let's see if you understood this. If you have y equals to 1, then it's a plane passing through 0, 1, 0, perpendicular to what axis?
X.
No. This one's perpendicular to the x-axis. I'm talking about y equals to 1. Y equals to 1 is a plane passing through 1, 0, 1, 0, and it's perpendicular to the y-axis. Right? What plane is it parallel to? Parallel to
the
xz plane, right? That's what it is. Okay, so once you understood that, then the next question is, what about y equals to x in 3D? What would that give us? Y equals to x. Now, you all know that y equals to x gives us a line in 2D, right? It's a 45-degree angle line. It's a diagonal kind of line, right? But what would that give us in 3D? Any ideas? Definitely, see in this, if I look at it in this 3D, y equals to x will contain all these lines, right? Here I'm saying that these two lengths are the same, okay? X and y coordinates are the same. But this doesn't say anything about the z. So z could be anything, right? So not only it's going to create this line, but it will create another line that's passing through any height, right? What would that do? Yeah?
It's another plane.
It's another plane that contains the z-axis, right? And it's cutting through the xy plane as the 45-degree line, right? Okay, so that one, it's harder to describe, but we'll later figure out a better way to describe this. So right now I'm trying my best to what we have. So this is a plane containing the z-axis and whose xy trace is this. XY trace means like the intersection between the XY plane and this plane. Whenever you have some kind of graph, you can talk about XY trace of that thing. It's like where they meet. And if you look at where they meet, that means Z is 0. So this just becomes a graph in the XY plane. And of course, we know that the graph of this thing on the XY plane is this, right? So imagine, one way to imagine this plane is just think of the z-axis that's coming from the board, right? And you just have this plane. That's the plane that we're working with. Is that good? Can you picture that? All right. So that's what we have. Now, it turns out that the easiest way to describe a plane is to talk in terms of its normal vector. So to say that it's perpendicular to something. So here, there's this vector that's perpendicular to this vector, this plane, right? What is that vector? That's like -1 and 1. So -1, 1, and then this vector doesn't go up or down. It's like if you have this plane, the perpendicular vector is also parallel to the xy plane, right? So it should be this one. So a better way to describe it would be a plane perpendicular to this vector, okay, passing the origin. And that's going to be the way we are going to describe things. So let me put forward a statement and see if this makes sense, okay? All right, so observation. AX plus BY plus CZ equals to 0 in 3D is a plane perpendicular to A comma B comma C and passing the origin 0 comma 0 comma 0. Okay. Let me try to explain why this is the case. The easier one is to see that it passes 0 comma 0 comma 0. How do you know that any point is on the graph? You just plug them in, and if the equal sign works, then that's a point on the graph, right? Yeah. So if you plug in 0, 0, 0, and here 0, 0, 0, you do get 0, and 0 is indeed equal to 0, so 0 comma 0 comma 0 is a point on the graph. Now, what if we plug in 1, 1, 1? Well, if I plug in 1, 1, 1, then that says A plus B plus C is 0. And that would be only true if indeed A plus B plus C is 0. So for example, if A, B, C were all 1s, then that 1, 1, 1 could not be a point on the graph, right? So that's the first thing that's easy to see. However, to see something's perpendicular, that's a bit more challenging. But then remember, we learned some vector operations, right? What vector operations easily tell us something's perpendicular? Orthogonal. Huh? If we have two vectors, how do you know if something is when two vectors are perpendicular? Yeah? The dot product, exactly. Yeah. So think of it like this. If you have A comma B comma C, so reason. If you have A comma B comma C as a vector, okay, and X comma Y comma Z as a vector, but X, Y, Z it satisfies this equation, so it's a point on the plane, okay? Yeah. So let's say X, Y, Z is a point on the plane, A, B, C is another given vector, and if I do a dot product of these two, let's see what that does. dot product is component-wise multiplication and add, right? So you end up with A times X, B times Y, C times Z. So we did the component-wise multiplication and we added them. What is that equal to? Equal to 0. If the dot product of two vectors are 0, what does that mean? Perpendicular, right? So you have A, B, C perpendicular to X, Y, Z. Okay. So that's the first thing that you understand about plane. Example 1. Find the equation of line, equation of plane passing 0, 0, 0 and perpendicular to 1, 3, negative. And although you can just directly use that as the formula, let me try to describe this and figure it out as if we didn't know that, okay? So what we have here is, let's say x comma y comma z is some point on the plane. So there's some plane. And this is definitely inaccurate. I really haven't thought about what exactly this direction is. But let's just say that this is the plane that we're going after, and this is a point on the plane. Okay. Now, because this plane also passes through the origin, this entire vector that starts at the origin and ends at x comma y comma z is going to be lying inside the plane, right? But at the same time, I know that this vector 1, 3, negative 1, well, actually, definitely it's the wrong direction because it's going down. But let's just say this is some strange orientation. Maybe this is z. Oh, who cares? Yeah. I think it makes a bit more sense if this is z, and if it's x, y, and z, that might make more sense. But that's not the point. It's just saying you have some vector that's perpendicular. Then what do we know? Then this x comma y comma z better be having a dot product with this vector as 0 because they're perpendicular, right? So we say that 1, 3, negative 1 dotted with x, y, z must equal to 0. Okay. And then that directly translates to 1x plus 3y plus negative 1z equal to 0. So that's it, that's the answer. If you want to simplify, you can write it like this. That's it. Okay, so hopefully that example explains this observation more clearly. But then the immediate question that you get right after this is like, what about planes that do not pass through the origin? Okay? So let's try that one. Example 2. Find equation of plane passing, let's say 2, 1, negative 2, and is perpendicular to negative 1, 5, and 3. Okay. Solution. So let's say here's 2, 1, negative 2. And you have a plane passing through that, and there's this vector negative 1, 5, 3. And let's say there's some point on the plane x, y, z, and my goal is to find the equation that x, y, and z would satisfy. Do you agree with this? This is what we want, right? We want this to be perpendicular. That's all we want, okay? And that should give us an equation for x, y, and z. Any questions so far? Now what we do is we have to say that this vector, negative 1, 5, 3, and this vector are perpendicular, just from the picture. But what is this vector? To get a vector going from initial to terminal, how do you get the vector? You always have to do terminal minus initial, right? That's how you get the vector. Is that good? All right. So what we have to say is that negative 1, 5, 3 dotted with this new vector, which is x, y, z, minus, that's the terminal, minus the initial, which is 2, 1, negative 2, has to equal to 0. And let's see what that is. That's equal to negative 1, 5, 3. It's x minus 2, y minus 1, and z plus 2. So that if you multiply component-wise, this is the dot product, sorry. If you do component-wise multiplication and add, that gives you negative 1 times x minus 2, plus 5 times y minus 1, plus 3 times z plus 2, and then that has to equal to 0. So you have negative x plus 2 plus 5y minus 5 plus 3z plus 6 equals to 0. And then negative x plus 5y plus 3z. And then 2 minus 5 is negative 3 plus 6 will be positive 3 equals to 0. Now usually what you do is you want to put this constant on the other side. And negative x plus 5y plus 3z equals to negative 3 as your answer. And note ax plus by plus cz equals to d is called the standard form of a plane equation in 3D. Okay? So that's the answer to this. And once you've done one example, you can actually figure out the generic formula for plane equations. So let's summarize the findings by this formula. So formula for plane in 3D. Okay? It's a x minus x1 plus b times y minus y1 plus c times z minus z1 equal to 0. Okay. Now what is this? This is the plane passing x1, y1, z1 and is perpendicular to, let's say perpendicular to ABC. We call A comma B comma C the normal vector for the plane. Now this is slightly wrong because if you have a plane, there are so many different normal vectors, right? Because normal vectors can have like many different lengths, and it can also have like a normal vector that direction, also a normal vector the other direction. So there isn't a single normal vector, but I'll just write it that way. And so the coefficients, whenever you see these coefficients, negative 1, 5, and 3, that's the normal vector for this plane. Is that okay? Whenever you see an equation like this, then negative 1, 5, 3 written as a vector, that's the normal vector to the plane. Okay? And then it's easy to check that x1, y1, z1 is a point on this graph because if you plug in x1 into x, y1 into y, z1 into z, what do you get on the left side? Let me ask the question again. If you plug in x1 into x, y1 into y, z1 into z, what do you get on the left side?
0.
0. Is 0 equals to 0?
Yeah.
Of course. What does that mean? What did we just verify? That this given point is a point on the graph. If you plug in a point and it satisfies the equation, it's a point on the graph, right? Okay, so that's why this is a point on this graph. Perpendicular has to do with like ABC dotted with this vector, this comma this gives you 0. But that wasn't what I was trying to explain. If you plug this into the left side, you get 0 equal to 0, so this is a point on the plane. Okay, suppose you came into this class late, okay? So just as I'm erasing this, you just sat down and you just saw this, and you have no idea what's going on. Now, is there a way to figure out what kind of plane this is without having to know all these languages? Well, there's a totally different approach to seeing that this is a plane, and that's about finding the traces. Okay, so xy trace, yz trace, okay? So let's talk about that. What is the xy trace? So we're investigating this one. Negative x plus 5y plus 3z equals negative 3. So what's the xy trace? That's when you set z equal to 0, so that z is gone and you just have x and y. And that gives you the intersection between the said object and the xy plane. And of course, this is a line. But what kind of line is it? It's a line with slope negative 1/5 and y-intercept negative 5/3. So looks like here's x, here's y. Here's negative 5/3. Let's say here's negative 5/3, and then it's a line that's like this. And then what about the yz trace? Yz trace would be setting x at 0. That gives you 5y plus 3z equals to negative 3. And if I solve for z, this will be negative 5/3 y, and then this will be minus 1. So if I have the z-axis and the y-axis, here's negative 1, and then you have this. And then you can also get the xz trace, which is setting y as 0. And that gives you negative x plus 3z equals to negative 3. So z is equals to negative 1/3, actually positive 1/3 x minus 1. And that gives you negative 1, and then it's something like this. If you put this together, here's z, here's x, here's y. For the xy trace, you have this guy here, which is like that on the xy. Okay. On the yz trace, it's this. So It's like it's like this. Okay, they should meet. And then on the XZ trace, it should be like this, and they should meet. So you can say that here's -1. What's the, this will be -1, this will be +3. Oh, sorry, that's wrong. XC. Yeah, the problem is here, XX is on the right side, but here the XX is on the left side, right? So unfortunately, it's something like this. Yeah, so it's some kind of a plane that's passing through these points. Okay. So I'm just saying that there's a way to make sense out of that by looking at the XY trace and YZ trace and ZX trace. All right. So that's it. So you just have to remember this formula. We did a lot of talking, but really it just boils down to remembering this one formula. That's all for the plane equation. But now let's go to lines. If these things are planes, how are you going to get lines? Well, for lines, you have to do a totally different approach. And for the lines, you do something like x equals to AT plus x1, y equals to BT plus y1, and z equals to CT plus z1. And I'll try to convince you that what you're seeing is a line equation, the parametrized version of the line equation. Now, what does this equation mean? Well, what this means is that for each time t, you have three numbers, x, y, and z, the position of a moving particle. So you may remember the moving particle rectilinear motion in calculus 1, right? Yeah. And at every time, if you just had this, at every time you're given the location of the moving particle, right? Moving at a straight line. Right? So it's something like this, but now this particle is moving in 3D, so it's a particle that's moving in 3D. Okay? It has three numbers, so it's a particle moving in 3D. So imagine like this. Let's say at time t goes to 0, at time t equals to 0, let's say you have some point x1, y1, z1. That's where the particle is at time t equals 0. And then at time t equals to 1, if you plug in 1, the value changes, right? So at time t equals to 1, it's at some other point. At time t equals to 2, it's again at another point, right? And although in physics you can't plug in negative time, let's just plug in negative time as well. So to be a full line, you really need the t to go from negative infinity to positive infinity, okay? So time t equals to negative, back to the future. Yeah. If you go back in time, then there's other places. So what you're seeing should be thought as a trajectory of a moving point, okay? if you plot all the points for all the values of t, I claim that this is a line. Okay? So now I have to argue why that's a line. The way you see it, the easiest way to see it is to just differentiate these with respect to t. Okay? So what do you get if you differentiate this by t? Simple question. Just a, right? T differentiates to 1, that's a constant, so that goes away. So you just get a, right? If you differentiate this, what do you get? B. If you differentiate this by t, you get c. And you get a comma b comma c as the values of the derivatives. Now, because x comma y comma z is a position, what do you get if you differentiate position? It's a rate of change of the position. What is that called?
Velocity.
Velocity, yes. Very good. So, if you have position, and if you differentiate this by t, you get velocity. Now, there's a slightly different notion in physics, which is called the distance traveled. And if you differentiate this, guess what you get then? Guess what you get? It's a related quantity, but it's slightly different.
Speed.
Yeah? Speed, yes, speed. The difference between these two is that position is a vector. X comma y comma z. It has 3 numbers. So at every time, it gives you a position vector of that moving particle. You get that? Okay. A position vector is where you assume that the beginning point of the vector is at 0, 0, 0, and the terminal point of the vector, in that case, holds the data about where the location of the particle is. Okay, so the position vector is what you're given, and because you're differentiating a vector, which means you're differentiating individual components, you get another vector. So you get a velocity. Right? On the other hand, distance traveled is like how far something moves, right? And the distance traveled is always a number, a single number, because it only measures the length, right? So if you have something that's going like that, a position vector will be the location of this final point, but the distance traveled would be the length of this curve. So it'll be a single number. And because this is a scalar, it's a single number. If you differentiate, you get a single number, so you get a scalar value. It does measure how fast you're moving, but it's a scalar. So what is that? That's speed. So you have to know these two differences, right? But now coming back to this, notice that ABC is a constant. So if you have a moving particle and you differentiate it and you got a constant velocity, what kind of motion is that? It's constant velocity motion, right? Now, there's a big difference between a constant speed motion and constant velocity motion. What's the difference? Yeah?
Because going at the same speed in different directions.
Yeah, constant speed could mean that you're changing the direction, but just moving at a constant speed, right? Yeah. On the other hand, constant velocity means you don't even change the direction. If you're moving in one direction without changing direction, what will be the shape of the trajectory? Huh?
Straight line.
Oh, a straight line. That's why this is a straight line. Okay, are you convinced? All right, that's why this is a straight line. Think of the circular constant speed motion. There's certainly something like that, right? Yeah. Earth is almost that, but it's not really circular. It's a ellipse, so it actually accelerates. It's faster when it's closer to the sun, and it's slower when it's further away. So it's not really that, but there are cases where you can think of a circular motion that's all a constant motion, right? Constant speed motion. Yeah, constant speed motion means you could still change the direction, but if you have constant velocity motion, that means you can't even change the direction, so you have no choice but to go straight. Okay, and that's why this will give you a straight line if you drew the graph for all the values of t. Agreed? Okay, now, so that's why this is going to give you a straight line. And if you look at the velocity will be in the direction of that the line is moving, right? The particle is moving. So the velocity that you get A comma B comma C will now be the tangential direction of the movement, right? So velocity is always the tangential direction of the movement. In this case, it is embedded in the line itself because it's exactly the same as the direction that the line is going. So in such a case, we have a name for this. So with all the descriptions that I tried, you can say that A, B, so the above equation, so it's not above, but it's over here, but I'm assuming that you're taking notes. Okay, so if this is above this one, the above equation is a line in 3D whose direction is A comma B comma C and passing x1 comma y1 comma z1. And the reason that we know that x1, y1, z1 itself is a point on this line is because if I plug in t equals to 0, it gives you the three numbers, x1, y1, z1. Okay? So this is the formula. And this formula is called the parametric form. Okay, so let me put a question. Example 3. Find the equation of the line passing (1, -2, 3) and is parallel to the vector 5, 2, and then -3. Okay. And the answer is simply, it should be x, y, z. It's 5t plus 1 for the x component, 5t plus 1, right? It should be y equals to 2t minus 2, 2t minus 2. And for z, it would be -3t plus 3. Now, let's just check. If you differentiate this function, this position function, what do you get? 5, 2, 3. 5, 2, -3. Exactly the same vector, right? And if you plug in t equals to 0, what do you get? You get 1, -2, 3, exactly this point. So we know that this is a straight line with this direction passing through this point. And that's the answer. Simple, right? Any questions? But now, some people might not like this equation because it has an extra t. So now the next question is there a way to remove t and write down the equation in a different way? And the answer is yes. You can rewrite this equation in a form that doesn't have t in there. So how do you do that? Well, if we solve the above, again, it's not above, but for this one, I'm assuming this is above here. For t, we get, let's see what we get. So first of all, x equals to 5t plus 1. We can subtract 1 both sides. And then now we can divide by 5, and you get x minus 1 over 5 equals to t. Okay, y equals to 2t minus 2. So if I add to both sides, I get y plus 2 equals to 2t. Divide both sides by 2, you get y plus 2. Divide by 2 equals to t. And then try to do the same thing for z. Solve for t. Can you do that? Yeah.
I just noticed if you do 2 times y plus 2 over 2, you just get y plus 2 minus 2, which is equal to y. So, why are we getting rid of the t?
We haven't gotten rid of the t yet. I'm just solving for t for now.
I would say if you plug in like what you got for t into it, you just
Yeah, of course. Like it's this
Yeah.
this is same thing as that. So if you replace y by that, you just get t equals to t. Yeah. So,
you just get y.
but that's not my point. Yeah.
Okay.
That's something that's it's same, so it's not a surprising result. T is always t, so it's not a surprising result. All right, so we can do the same. Subtract 3, and then divide by -3. So you have z minus 3 over -3 equals to t. Now it's customary to multiply negative, so that you write this down as 3 minus z over 3. That's the usual way that people like to write because they don't want to have a minus in the denominator. But we'll just leave it at that, okay? Now, once you solve everything for t, and there's something you can do. You can say x minus 1 over 5, since that's equal to t, and y plus t 2 over 2 is also equals, they're both equal to t, right? So they must be equal. Agreed? And because this is also equals to t, you can say this is equal to z minus 3 over -3. Okay, so you have two equations. You have this equation and another equation. And supposedly that gives you the line. Okay. Now, why is that? Well, do you have a question? Is there?
Yeah. It says y equals 2t minus 2.
Yeah.
And then y plus 2 equals negative 2t. Shouldn't it be a negative 2t on the right side?
No, I added to both sides.
Oh, okay.
So y plus 2 is just 2t. Yeah. Okay, so now we have to convince ourselves that this is also a line equation. Why is that? Well, you have x minus 1 over 5 equals to y plus 2 over 2. What is that? If you just had this, what do you get in 3D? Huh? A plane. In 2D, this will be a line, but in 3D, this will be a plane. Isn't that right? Yeah. It's going to be a plane that's perpendicular to the z-axis. Okay. Okay. What about this? What would that give us? Just this, without that. Just this. Again, it will be a plane, this time perpendicular to the x-axis, right? So you have two planes, right? And you're saying that they're both true, so the values of x and y and z that satisfies both will be in the intersection of two planes. Now, if you have two planes intersecting in 3D, what do you get?
A line.
A line. You get a line. Yeah. So that's why this is going to give you a line. Okay? So as weird as it seems, if you want the line, you can't just write down a single equation for a line in 3D. You need two equations at least to give you a line in 3D because a line in 3D is made by intersecting two planes. Each plane looks like a single equation, right? So you need two equations to give you a line. Is it okay? Now, this new form, notice that this one looks like the following. If you have x1, y1, and z1 as a point on the line, and A comma B comma C as their direction vector, just like there, then this looks like this, right? See, 5, 2, negative 3, that's exactly 5, 2, negative 3, isn't that right? Yeah. And then what about this one? It's x minus 1, and think of this as x minus negative 2, and think of it as x minus 3, so it's 1, negative 2, 3, which is exactly this point, right? So you see that the formula for a line equation without the t is this one. And such a form is called a symmetric form. So you have, so summary is if ABC is direction and x1, y1, z1 is a point on the line, then equation of this line in 3D can be written in two ways. So number one, there's the parametric form, which is x is equal to at plus x1, y is equal to bt plus y1, z equals to ct plus z1. And secondly, there's a symmetric form, which is x minus x1 over a equals to y minus y1 over b equals to z minus z1 over c. Okay? Any questions? Do you have any questions? Okay, since nobody has a question, let me ask, what if A or B or C is 0? What do we do then? So what if, say, ABC, the direction vector is, say, 1, 1, 0? What do you do in that case? In that case, the symmetric form will look very different. And remember, how did we get this? We just took the parametric form and solved for t, right? So, question, what if ABC is 1, 1, 0? And just for convenience, let's just say x1, y1, z1 is 1, 2, 3. Well, in that case, ignore the fact that you have this formula, just go for the parametric form, which says x equals to 1t plus 1, y is equal to 1t plus 2, and z is equal to 0t plus 3, right? And then you try to solve for t, just like you did before, right? Which is, this one will say t is equals to x minus 1. This one is going to say t is equals to y minus 2. But this one is just z equals to 3. You can't do anything about it, right? But then you can still get rid of t just by setting these two equal. So the outcome is that the symmetric form will now look like x minus 1 equals to y minus 2, comma, z is 3. Okay. In other words, the line that we're trying to get, this line that we described as parametric form, if you try to write it without the t, it's an intersection of this plane with that plane. That's a plane, so the intersection will be a line, right? Okay. So, in most cases, A, B, C are not 0, and this is perfectly fine, but sometimes this formula will fail. In that case, you have to do something like that, okay? All right, so we got all the formulas down, but we're still far from being done because there's so many different possible questions I can ask you.